Welcome to Advanced Group Theory. Today, we are going to explore a fascinating concept called conjugacy classes. If you have ever wondered how mathematicians group together actions that are fundamentally the same, even when they look different on the surface, you are in the right place. Let us dive in and see how this works. To understand conjugacy, imagine you have a special physical action, like performing a backflip. If you do a backflip facing north, that is one specific action. Now, imagine you first turn to face east, do the exact same backflip, and then turn back to face north. The core action, the backflip, is exactly the same, but it was performed in a different context. In mathematics, a group is a set of elements combined with a rule. Within a group, we often want to bundle together actions that are fundamentally the same, even if they look slightly different because of the starting perspective. This is exactly what a conjugacy class captures. Now that we understand the idea of the same action from a different perspective, let us translate this into formal mathematics. In a group, we say that an element A is conjugated to another element B if we can find some third element G that links them together. The mathematical link is the equation G times A times G inverse equals B. Here the element G represents the change of perspective, like turning to face east. The element A is the core action, the backflip, and G inverse is the undoing of that perspective change, turning back to face north. The result B is the final observed action. If you change G, you might get a different B, building the whole conjugacy class. Before we move on to an example, let us see this with a concrete visual diagram. The diagram you are looking at visually summarizes the core concept of conjugacy. Instead of performing action B directly at state Y, you can travel to state X using the path G inverse, perform action A there, and travel back to Y using path G. Both paths achieve the exact same final result. This proves that action A and action B are fundamentally the same action, just viewed from different locations in our space. This geometric intuition is incredibly powerful. Now that we have our formula and visual intuition, let us apply it to a concrete example. We want to find the conjugacy class of the element 1, 2 in the symmetric group S3. This group consists of all possible permutations of 3 items. To find the conjugacy class, we must calculate G times A times G inverse for every single element G in the group. Let us test a specific element, the swap 1, 3. We substitute these into our conjugacy formula. Because swapping the same 2 items twice puts them back in their original order, the inverse of 1, 3 is just 1, 3. This simplifies our expression. Continuing with our calculation, we now perform the permutation multiplication from right to left. We need to track where each number goes step by step. Starting with the number 1, the rightmost permutation sends 1 to 3. The middle permutation leaves 3 alone, and the leftmost permutation sends 3 back to 1. So ultimately, 1 goes to 1. Since 1 maps to itself, it will not appear in our final cycle notation. Next, we track the number 2. The rightmost leaves 2 alone, the middle sends 2 to 1, and the leftmost sends 1 to 3. So 2 goes to 3. Let us finish tracking our numbers. Finally, we track the number 3 through the sequence. The rightmost permutation sends 3 to 1. The middle permutation sends 1 to 2. The leftmost permutation leaves 2 alone, meaning 3 ultimately goes to 2. Since 2 goes to 3 and 3 goes back to 2, this forms the closed cycle 2, 3. This calculation proves that the swap 2, 3 is in the same conjugacy class as 1, 2. If we repeated this for every element, we would find that elements with the same cycle shape always belong to the same conjugacy class. So, we have successfully found a conjugacy class in an example. This brings us to an important theoretical question. Do these classes neatly divide the entire group into non-overlapping families? To prove this, we must show that conjugacy is an equivalence relation, which requires reflexivity, symmetry, and transitivity. First, we prove reflexivity, meaning every element is conjugate to itself. This is the simplest property to prove. We just use the identity element, which represents the do-nothing action. Since multiplying by the identity changes nothing, the equation holds perfectly true. Therefore, every element is indeed conjugate to itself, satisfying the first requirement. Continuing our proof, we now move to the second property, symmetry. We need to show that if A is conjugate to B, then B must be conjugate to A. We start with our standard assumption that A and B are linked by some element G. To reverse this relationship, we need to isolate A. We do this by multiplying both sides of our equation on the left by G inverse and on the right by G. By applying the associative property, the terms on the left side cancel out because any element multiplied by its inverse gives the identity element, leaving A completely by itself. Now that we have isolated A, we want to make this look exactly like our standard definition of conjugacy. To do this, we use a small trick. We rewrite G as the inverse of its own inverse. This helps us match the exact pattern required by the formal definition. Let us define a new element H, which is just G inverse. Since G is in the group, its inverse H is also guaranteed to be in the group. Substituting H into our equation gives us A equals H times B times H inverse. This perfectly matches the definition, completing the proof for symmetry. We are almost there. The final property we must prove is transitivity. This means if A is conjugate to B and B is conjugate to C, then A must be conjugate to C. We start by writing down our two assumptions as equations. The first links A and B via the element G. The second links B and C via the element H. To bridge the gap between A and C, we simply substitute the expression for B from our first equation directly into the second equation. This gives us a new, longer equation that we now need to simplify in the next step. To simplify our combined equation, we use the associative property to regroup the elements. We also apply the rule for the inverse of a product, which tells us that G inverse times H inverse is exactly the same as the quantity H times G all inverse. This allows us to combine the outer elements into a single term. Let us define a new element K as H times G. Because the group is closed, K is definitely in the group. Our equation becomes K times A times K inverse equals C. This proves transitivity and confirms that conjugacy classes perfectly partition the group into distinct, non-overlapping slices. Now that we have proven the core properties of conjugacy, let us look at how it applies to a different kind of group. We can take these abstract group theory concepts and apply them to concrete grids of numbers, specifically the group of all invertible 2x2 matrices. In linear algebra, an invertible matrix represents a geometric transformation, like a rotation or a stretch that can be undone. By looking at conjugacy in this context, we will uncover the beautiful geometric meaning behind the algebra we have been doing. It is the exact same logic, just applied to a new mathematical object. Let us see the formula for conjugacy when applied to matrices. We use the exact same definition, but we replace the abstract group elements with concrete matrices. The equation becomes P times A times P inverse equals B. Here, A and B are our core matrices that we are comparing. The matrix P is an invertible matrix representing a change of basis. This is exactly like looking at the same object from a different angle. P inverse is the matrix that undoes that change of perspective. In linear algebra, this exact equation is known as matrix similarity. If you change the basis matrix P, you are simply viewing the transformation A from a new coordinate system. Because similar matrices represent the same underlying geometric action, they must share many fundamental properties. One of the most important is the determinant. The formula shows that the determinant of matrix A will always perfectly equal the determinant of matrix B. The determinant measures how much a transformation stretches or shrinks an area. This physical stretching should not change just because you look at it from a different coordinate system. They will also share the same eigenvalues, which are special stretching factors, and the same trace. This proves that conjugacy classes group together matrices that are physically doing the exact same thing. You might be wondering, why do conjugacy classes matter outside of pure mathematics? In physics, particularly in quantum mechanics and particle physics, conjugacy classes are absolutely essential for understanding symmetries. When physicists look at the symmetries of a crystal or a molecule, the operations that belong to the same conjugacy class represent the same physical type of rotation or reflection, just along different axes. For instance, rotating a molecule by 120 degrees clockwise or counterclockwise belongs to the same class. Furthermore, they are the foundation of character theory, a powerful tool used to simplify complex quantum equations that would otherwise be overwhelmingly complicated. Let us summarize what we have learned today. The most important idea is that a conjugacy class groups together elements of a mathematical group that perform the exact same fundamental action, just from different starting perspectives. We test this using the formula G times A times G inverse equals B. We also proved that conjugacy is a valid equivalence relation, meaning it perfectly partitions any group into distinct slices. Finally, we saw that in linear algebra, this is known as matrix similarity. Understanding these classes allows mathematicians and physicists to break down massive, complicated groups into smaller, manageable families of similar behaviors. You now have a solid foundation in conjugacy classes.